Welcome to a screencast on acids, bases, and conjugate pairs. The objectives of this screencast are to state the Arrhenius and Bronsted Lowry definitions of acids and bases, to identify acids, bases, and conjugate acid-base pairs, and to write equations for acid and base ionization reactions, including predicting reaction products. When we deal with acids and bases, there are a number of definitions that we can use. Probably the most common definition of acids and bases is known as the Arrhenius definition. It's named after the Swedish scientist Svante Arrhenius, who was awarded the 1903 Nobel Prize for Chemistry. And according to the Arrhenius definition, an acid is a substance that produces hydronium ion in aqueous solution. Now, as a note, hydronium ion is what's actually produced by an Arrhenius acid. We sometimes use H plus as a shorthand for H3O plus, even though it's technically not correct. More on that in a little bit. In the Arrhenius definition sense, a base is a substance that produces hydroxide ions, OH minus, in aqueous solution. A couple examples. HCl is a gas. When it dissolves in water, it produces H3O plus, hydronium ion, as well as chloride, and producing H3O plus is what makes HCl an Arrhenius acid. Here's the shorthand way of writing it. HCl dissolves in water to make H plus and Cl minus, and again, the H plus that's produced immediately combines with H2O to make H3O plus, so that's more correct, but H plus is sometimes used for shortcut. Now, NaOH is a solid. When that dissolves in water, it produces, along with sodium ion, a hydroxide ion, and producing the hydroxide ion is what makes NaOH an Arrhenius base. Now, a more general way to look at acids and bases is using what's known as the Bronsted Lowry definition. And Johannes Bronsted, a Danish chemist, and Thomas Lowry, an English chemist, in 1923 both arrived at the same way of looking at acids and bases. They did this independently. And so the Bronsted Lowry way of looking at acids and bases is that an acid is a substance that donates a proton. We call it a proton donor. And very important to note, a proton is a hydrogen atom that has lost its electron, so it's a hydrogen ion. And a base, according to Bronsted Lowry, is a substance that accepts a proton. We call it a proton acceptor. And notice an acid and a base are chemically essentially exactly opposite each other. One is a proton donor, one is a proton acceptor, and this way of looking at acids and bases is more general than the Arrhenius way because we don't have to deal with aqueous solutions, and it's very useful in a whole bunch of different contexts, which we will start to explore next. An example, HCl, which is an Arrhenius acid. Hopefully it's also a Bronsted Lowry acid. And when HCl dissociates into H plus and Cl minus, the forming H plus, donating an H plus or a proton is what makes it a Bronsted Lowry acid. And then the OH minus that's produced by NaOH in water, the OH minus can accept an H plus or accept a proton, and so OH minus is a Bronsted Lowry base because it can accept an H plus, and when it does, of course, it makes H2O. Now, we can use these concepts to apply them to acid-base reactions, and you've probably seen acid-base reactions before. For example, HCl, the acid we just dealt with, reacts with NaOH, the base we just dealt with, to produce NaCl and H2O. And we often talk about an acid-base reaction in aqueous solution in general as being an acid that reacts with a base, and we'd say the acid is neutralized by the base, or the base is neutralized by the acid, and a salt and water are produced. And this is true, but this applies to aqueous solutions, and we'd like to look at acid-base reactions more generally. So we're going to move away from using the Arrhenius definition of an acid producing H3O plus and a base producing OH minus in aqueous solution, and we're going to apply the Bronsted Lowry proton donor, proton acceptor way of looking at things. This is more generally useful. And to do that, we'll introduce a concept known as acid-base conjugate pairs, and let's look at this first with just the acid HCl, but in aqueous solution. So HCl with H2O makes H3O plus and Cl minus. We have seen this already. And if we look at things on a molecular level, HCl is a hydrogen atom bonded to a Cl atom. It's a gas normally. We dissolve it in water. What happens is the H and the Cl break apart, and one thing that's produced is a Cl minus, a chloride ion. Now, notice that the HCl and the Cl minus only differ by an H plus. The HCl is an acid because it donates an H plus. The H plus from the HCl is donated to the H2O to make H3O plus. And the Cl minus that's produced we call the conjugate base of HCl. Notice if we were able to go in reverse on this reaction, and we don't, we can't because HCl is a strong acid that fully dissociates, but if we could, Cl minus could accept a proton from the H3O plus to make HCl, and if it did that, it would function as a base. So HCl is an acid, Cl minus is its conjugate base, and together we call them a conjugate acid-base pair. Now, there's another conjugate acid-base pair in this reaction, and H2O on a molecular level looks like this. It accepts the H plus from the HCl, and when that happens, it produces H3O plus. And so this pair of substances only differ by an H plus as well, by a proton, and H2O accepts a proton from HCl, so it's a base, a Bronsted Lowry base, and the H3O plus is its conjugate acid. And again, if we could go in reverse, H3O plus could function as an acid by donating a proton to the Cl minus, and so H2O and H3O plus are another conjugate acid-base pair. And in general, we can look at acid-base reactions in terms of pairs of conjugate acids and bases, each of which differ just by a hydrogen ion or a proton, and the reaction itself or the process itself involves transfer of a proton from one substance to another. Now, here's the molecular level image we just looked at. We can also look at this from a Lewis dot perspective, maybe gives us a little bit of deeper understanding. HCl, H2O, H3O plus, and Cl minus. Here are the Lewis dot structures. And the H from HCl is pretty happy to attach to a lone pair of electrons on the H2O. And so HCl donates a proton to the H2O. H2O accepts the proton. Going in the opposite direction, if it would happen, H3O plus could potentially donate a proton to the Cl minus, and then H3O plus would function as an acid and Cl minus would function as a base. And so from left to right, HCl would be a proton donor and H2O would be a proton acceptor. And going from right to left, H3O plus would be a proton donor and Cl minus would be a proton acceptor. And we're going to apply this to all kinds of different acid-base processes, including ones that reach equilibrium, that's not completely product favored or completely reactant favored. And again, just as a note, these are conjugate acid-base pairs. Okay, so here is an acid that is not a strong acid. Hydrofluoric acid is a weak acid. It only partially dissociates in water. It produces F minus and H3O plus. It's an Arrhenius acid because it's producing H3O plus. And on a Lewis dot structure level. Here are HF, H2O, F minus, and H3O plus. And HF can donate a proton to H2O. That produces F minus and H3O plus. But in this case, F minus can actually also accept a proton from the H3O plus and produce HF and H2O. And so HF is an acid because it's a proton donor. H2O is a base because it's a proton acceptor. F minus is the conjugate base of HF, and going from right to left, it could function as a proton acceptor. And H3O plus is an acid. It's the conjugate acid of H2O, and it can function as an acid because it can lose or donate an H plus. And so HF and F minus are one conjugate acid-base pair, and H2O and H3O plus are the other. And one more. Let's deal with a base. NH3 in aqueous solution makes NH4 plus and OH minus. And NH3 is a base in the Arrhenius sense because it produces hydroxide ion in aqueous solution. And in the Bronsted Lowry sense, if we look at our molecules, NH3 has a lone pair that can accept a hydrogen from the H2O. And that will make NH4 plus and leaves an OH minus. And so we can have a proton transferred from H2O to NH3. That means that NH3 is a Bronsted Lowry base and H2O is a Bronsted Lowry acid. And going in the opposite direction from right to left, NH4 plus can donate an H plus to OH minus, making NH4 plus a Bronsted Lowry acid and OH minus a Bronsted Lowry base. And the conjugate acid-base pairs are NH3 with NH4 plus and H2O with OH minus. And again, a proton is being transferred from one substance to another, and the direction of proton transfer from left to right is opposite the direction of proton transfer from right to left. And in this case, we have an equilibrium position that is settled on, and this is something we'll explore more in future. So that's it for the acids, bases, and conjugate pairs screencast. And that's it for acids, bases, and conjugate pairs.